Okay, so last time we started looking at the difference between density and number, and we talked about a very simple system which you can think of as being a lattice gas. So at the top here, excuse me. At the top here, we have a lattice with sites specified by integers and particles labeled by numbers, also integers, 1, 2, 3, 4, shown at the top. Particle labels in blue, site labels in orange. And if we wanted to know what is the number of particles at site X, so you tell me what is the site, and then I'll tell you how many particles are there. In principle, you could have more than one atom at a given site. So what we talked about was the idea that you can count with delta functions. So I write a Kronecker delta of x minus xi, and I sum over all the labels of each of the particles from 1 to n. That's the xi's on the right-hand side. And then whenever that Kronecker delta, the position that you've asked for, that's this position here, coincides with the position of a particle, that argument of the delta function is 0, and so the delta function then gives you a 1, and then you go on to the next particle, and you go on to the next one, and so on, and that way you find out how many particles are at the site I. So then we talked about, well, that's simple. So now let's think about particles on a continuum line. So that's shown at the bottom of the screen. So here I have a line where the position is specified as a real number. The particles are still labels. The particle labels are still integers, 1, 2, 3, 4, 5. And the microscopic density of particles at the position X is given by the formula that I've written at the bottom here, namely that I sum over all the particle labels and whenever the particle position xi, those are the particle labels, equals the lattice site that you have specified on the left-hand side. So you tell me what x is, and I tell you then I tell you how many times this delta function has a 0 argument. And when that delta function has a 0 argument, its value is, quote, infinity. But what that really means is that when I take that delta function and integrate it between x is equal to a and x is equal to b, let's say, so then what I get is this integral over here. And so here again is my particle labels. I've specified the lower limits a and b over here. And now when I do that integral, so we just simply expand it out. So I'm summing from I equals 1 to n of that integral. So that is equal to the first term, second term, and so on and so forth. And you can see that particle position x equals x1, that is outside of the area of integration. I'm integrating between a and b. So the integral never includes the position of particle 1. So that delta function won't give you an infinity and get counted. So that one gives you 0. And then particle 2 is within that range. So when I integrate this delta function between a and b, when I go past the position of this particle, I will then get a 1 from integrating that delta function. So this will give me a 1. And then when I do the same thing, I get to particle 3, I will also get a 1. Same thing with particle 4, I'll get a 1. Particle 5 is again outside of the range of integration, so that will give you a 0 and so on and so forth. And so in the end, I will have discovered that there are 3 particles within this position range between A and B. And that's exactly what we mean by density, because what is density? Well, it says if I know the density of a system as a function of x, I integrate over x over some volume omega, that gives me, that n will be the number of particles in the volume omega. And then that is just the integral dn by dv. And so the density is now, in this case, the number of particles per unit volume rather than the number of particles at a particular point in space. So that was a very simple concept of just looking at density in space. Anybody have any questions about that? Okay, so now we're going to, at the end of the last lecture, we started applying this to looking at energy levels and energy states in a quantum system. So we want to understand, for example, what is the entropy of a system, which is counting the number of quantum states. More precisely, we might say if I have a system with energy E, then I want to know how many quantum states are at that energy E. And as we talked about, that answer is going to be mostly zero, because mostly you choose a value of E, you'll just come up with some number, 17.35, and it's very unlikely that if I sum over the quantum states of all those particles, then I'm going to get a number exactly equal to the 17.385 or whatever it was that I came up with. And so I'll get zero, except every now and then I might guess a number E, which is in fact an allowed energy, and then I'll get something. So what we do instead is we count the number of particles between energy E1 and E2, and we're going to do that just like we did with the density in space, but now we're going to do it with density and energy. So now what we do is when we label the particles, on the left-hand side, and what we were doing before, we just gave the particles a name. Particles 1, particle 2, particle 3, and so on. Now what we're doing is we're labeling the particles not by an arbitrary name, but by their quantum state. The quantum state is the value of the quantum numbers nx, ny, nz for that particle in the system. And so there's a quantum state for each particle. And so what we do then is when we count the energy levels exactly at the energy E, we would end up with this formula over here, which is a Kronecker delta, which simply says just sum up the energy levels of the ideal gas, h bar squared over 2n pi over L squared n squared. And if that number happens to give you E, then great, you'll get a zero there, and therefore the Kronecker delta will give you a 1. But now we're a bit more sophisticated. So what we're going to be saying is, look, when we look at the energy levels of the particles, they're quantized over here in units of h bar squared over 2m pi over L squared, and then n, then the quantum states. So what's going to happen as I take a system that gets bigger and bigger and bigger, and eventually that size is going to be something like the de Broglie wavelength of the quantum particles. What's going to happen is the spacing between those energy states goes to zero. So over here on the left-hand side, I have discrete states. That's over here on the left. But over here on the right, as I take L goes from infinity, that spacing goes to zero. And now what I have is this picture on the left now turns more into the picture I've shown on the right, where I have a density of states, but now not over space, but over energy. And so that is the density of states in energy. So then really what that means is that when I go to the continuum limit, then in fact what I have is not a Kronecker delta, but a Dirac delta, and I have the formula shown over here at the top of the page. And what is that useful for? Well, it answers the question, what is the number of quantum states with energy between E and E plus delta E? Or it could be anything you want. And the answer is, well, all I have to do is integrate that with respect to energy. So we should perhaps call this a energy prime, a dummy variable. And we integrate that with respect to energy, and then that will tell us how many quantum states are in there. So what that means is that when we now start talking about entropy, we will be talking about the number of quantum states, not at energy E, but between E and E plus delta E, where delta E is some small measure of uncertainty in our measurement of energy. In fact, nothing will depend on what delta E is, as you will see, but that technically is what we're doing. Okay, so now everybody's here. So what I'm going to do today is I'm going to finish this calculation, which won't take me too long. There will be some manipulations in it that may be unfamiliar with you. I'm going to go through those. I won't I don't want to spend too long on the algebra. But afterwards, we have a discussion session in 2702, and then I'll go there with the grader, and I'll be happy to answer questions on the technical details of those things at that discussion session. Now, in the homework that I distributed after last week's lecture, I distributed on Thursday. So you have a bunch of questions there, and I gave you very specific instructions in the homework how to do them. So I will also be available if you want to ask me questions about that. And one of the questions in that homework actually involves basically doing the calculation I'm going to do in class today. So a very good use of that discussion session will be everybody comes to class and then just sits there and just works that homework problem, and you can ask me or the grade if you need any hints, and do it like that. Okay. Let me just say a few words about how to do homework. I did give you instructions on the thing. I want to make a few points clear. So putting aside questions about AI and things like this, let me say what is the best way to try to attempt homework problems. Okay. First of all of them have been chosen to make you think about the things I've talked about in class, but in ways that you might otherwise not have come to realize. So they're carefully chosen. They will teach you much more than you will learn by just sort of listening to the class and nodding politely. That's how you're going to really think. So that's the first thing. The second thing is there's two ways you can do homework. So let's look at the sort of Hollywood science fiction movie picture of what it is when a graduate student in physics is maybe about to invent a time machine or something, and they're going to go to the library and research their topic. And so you see the person going to the library, and the next shot you see on the screen is the student is surrounded by books and papers, and they're frantically going through all these books and trying to figure out what to do, and then they're doing their work. Okay, so that's Hollywood, and it looks great in movies, but it's absolutely useless if you actually want to learn anything. So don't be a Hollywood graduate student. Okay, here is a better way to do my homework. Well, my homework in particular, other people's probably also as well. Okay, the graduate students in Illinois used to call this the coffee shop algorithm. So the algorithm is you take the homework sheet and you take a bunch of paper, lots of paper, and you go to the coffee shop next to the physics department, and you don't take any computers, you don't take any phones or anything like that, and you just work through the problem. And so you'll be working through it, and then halfway through you'll say, "Damn, I don't know how I'm stuck." And maybe I don't know, you forgot what is the formula for the Hamiltonian, or what is the Schrödinger equation, or is there a minus sign here, or something like this. Okay, so too bad. Just go on to the next question. Do as much as you can, but make a note of what it was that you got stuck on. Okay, then you go back to your office, to your notes, to the textbooks, and you look now, what is the answer to that question? What is the sign of that term in the Hamiltonian, blah, blah, blah. Okay, you go and look it up and you say, yes, of course, that's what I forgot. Okay, great. I understand that now, it makes perfect sense. Okay, now you might then say, okay, fine, now I just sit down and finish the question. Absolutely not. Okay, you now go and look at all the other problems where you got stuck on. So you've got, say, 5 problems and you got halfway through each of them. So you look at all the things and you say, yes, that's the thing I didn't understand. That's the bit, why is that term there? Okay, there's this 2 pi over here. Whatever it is, you figure out the answer to the question. Then what you do, the thing that you'd forgotten. Then you go back to the coffee shop, okay? I probably want to pass through the restaurant on the way, but go back to the coffee shop, okay? And do it again, okay? Now work the problem again from the beginning. Work it all out. And hopefully this time, the point you got stuck at before, you won't get stuck at again, because you've just revised it and you've understood the thing that you'd forgotten. The reason you'd forgotten it is this: when you'd learnt it, you'd never understood the significance of what it was for. You didn't know what question it answered. So when you actually had to use it, you didn't realize, oh, that's the thing that I need. But now that you've realized, oh, this thing is actually useful because it tells me this, blah, blah, blah. So then you get to see how to use it, and your brain starts to assimilate the information. That is the best way to learn. You keep doing that, and it's a bit more time consuming, maybe. You then just say looking up the answer on the internet or on AI or whatever. But the thing about it is your understanding of physics will enormously improve. You will see that by the time you get to halfway through the quarter, you will be understanding more of the class, more of the questions. We'll need to go back to the library less and less. You'll start to be putting things together because you'll see the patterns, you'll understand how things fit together. That's the way that you learn. That's my goal, is to teach you how to do that. Okay. All right, so let's go back to what we're going to do in class. Yes.
Can you explain again what happens to the second sum in the delta function when you go to the continuous case? So now you're not summing over. Was that second sum for each particle, right?
Yes. So this thing over here, you're talking about this sum over here. So this term here, I'm going to talk about that in a little bit, but that term here is basically the analog of summing over the particle labels. Because the particles before were identified by 1, 2, 3, 4, 5. Now they're labeled by a three-dimensional vector, which has got 3 components in it, which tells you the quantum state of that particle. Does that make sense?
That was the case before the two, right?
There's what?
That was also the case in this with the hierarchy we were streaming.
Do you mean here?
Yeah. So what happened to that sum?
That that sum is here, but there's a slight misprint. So okay. So the particles are labeled by their quantum numbers. Okay, that's the name of a particle. So it's being particle 1, particle 2, it's particle with quantum number 2, 3, 6. Okay. Any other questions? Yes.
Just to clarify, the sum is not just summing each quantum number vector once. It's summing them by the number of particles that corresponds to that.
Each particle has a 3 vector associated with it, which is its quantum state, nx, ny, nz. And then you're going to be summing over all the integer values of nx, ny, nz, 1 to infinity. And you're going to be doing that for all the particle numbers. So if there's n particles, then there's 3n of those vectors. 3n numbers, I should say. Okay. All right, and we're going to talk about how you do that calculation in practice in a minute. Okay, so far it looks very formal, but now I'm going to show you how you actually do the calculation. Okay, let me tell you what else we're going to do today. We're going to do another thing today, which is I'm going to introduce you to a third principle, which is the principle of detailed balance. Okay, so everything we're doing in statistical mechanics right now, you've all heard of the Boltzmann distribution, right? Okay, I never mention it except to ask you, have you heard of the Boltzmann distribution, right? There's a reason for this. You never need it, okay? Everything you can, I want you to understand the simplest conceptual way to do statistical mechanics. And then we're going to see that the Boltzmann distribution is really just a trick to enable you to do the calculation in a more convenient way, okay? So we're not mentioning that. We're going to do everything by ad hoc methods, just based on these basic principles that I've told you about. So the principle of detailed balance, I'm going to explain that to you. It's going to be another statement about equilibrium and quantum states. And we're going to use it to derive the single particle distribution function for fermions. We're literally going to look at the collisions of particles, and we're going to see that from that we can derive laws of statistical mechanics. Okay, so let's get started then. What I want to do first of all is I want to evaluate these integrals to work out the entropy of a system. So let's get started with that. So now our goal, and okay, getting my notes here. Okay, so now what we're going to calculate is this formula for gamma of E or d gamma by dE. So we're going to calculate the entropy, and this entropy is going to be the entropy for how many particles are within E plus delta E minus the entropy of particles E. So we're going to be looking at the number of states between E plus delta E minus the number of states at E, and that I'm going to write as d gamma by dE times delta E. And so if I want to compute how many states there are between E1 and E2. So what I have to compute is the 1 over n factorial, the sum over the quantum numbers being positive definite, and then the integral from E1 to E2 delta of E prime minus h bar squared over 2m pi over L squared ni squared d E prime. So that's the answer. And when this delta function over here, this is a single delta function. It's a delta function of a scalar variable E. So if I'm integrating if I integrate a delta function, well, let me write it. Maybe I should write it like this. I can think of a delta function as the derivative in space, or dx, with respect to what's called the Heaviside function x, and theta of x is equal to 1 if x is greater than 0, and 0 if x is less than or equal to 0, like that. So if I differentiate that function, that then gives me a delta function. So when I integrate this delta function over here on the left-hand page, if I integrate the delta function, that just gives me a Heaviside function. So what that means is that this d gamma by dE delta E is 1 over n factorial and then my sum over n's greater than 0, and then it's going to be the Heaviside function of E minus h bar squared over 2m pi over L squared n squared. So we're going to go and work that out. Now, let me now tell you about two simplifications that I want to show you so we can actually do these integrals, to do these sums. So two simplifications. So the first simplification is that you can see that the argument of the density of states in energy, d gamma by dE, is something to do with Ni squared. Okay, you have this Ni squared occurring over here in all of these functions here. So summing over n greater than 0 is kind of inconvenient, but summing over all of n is easy, because we can eventually what we're going to do is turn the sums over n into integrals over n. So what we're going to do is that since this is an even function, what that means is the sum over n greater than 0 is equal to 1/2 the sum from all n. Okay, because I'm summing over positive ones, I'm going to ignore the one when n is equal to 0, because when n is equal to 0, it gives you 0 in this thing in any case. So as long as energy, I'm looking at energy equals 0, I can just say that summing over n being positive is the same as summing over n from minus infinity to plus infinity. So that's the first simplification, but I've got how many factors of half do I get? Well, how many factors of 1/2? Well, I have 1/2 for each dimension. For each particle, I have x, y, and z. So that's 3. So I have 1 over 1/2 cubed. That's each, the 3 is for nx, ny, and z for each particle. But then I'm multiplying all of these sums together. And so there's also going to be raised to the nth power because I have n particles. And when I write down this sum over all the n's, this is the sum over the n particle 1, the n's of particle 2, and so on up to particle n. So therefore, I get all those factors of half raised to the power 1 over 2 to the 3n. But the great thing about that is, once I've done that, then I can do an unrestricted sum over all quantum numbers, positive and negative. So that's the first thing. That's simplification number 1. Simplification number 2 is a very interesting one. That is, nobody likes to do summations, okay? Summations are hard, okay? Integrals are easy. You've spent the last 10 years in school and university learning how to do integrals, okay? So we always want to do things in integrals. So we want to turn the sums into integrals. So if you were to look at this, at the kinetic energy of the particles, so we've got these terms, h bar squared over 2m pi over L squared n squared. Okay, that is the kinetic energy. And another way to write it would be to say, well, let's define a wave vector k to be pi over L times nx, ny, nz. So that's the k vector. This is h bar k has the interpretation as being the momentum of the particle with wave number k, and this is so this is just basically this kinetic energy is just p squared over 2m. So so we're going to just turn the sums over k into integrals over k. So we're going to turn the sum over n into integrals over k. So let's now discuss how we do that. So if I want to think of the when I'm doing the sum over n, I could say the sum over n is basically like an integral over n, and then that integral over n, roughly speaking, then is going to be equal to dn by dk. That would be in just one dimension. So dn by dk is 1 over dk by dn. So let's have a look at what dk by dn is. Let's just for now make it one dimensional. So I've got k is pi over L times n. So that says that dk by dn is equal to pi over L, which means dn by dk is equal to L over pi. Okay, that's just very simple. So now if I do it in d dimensions, then I have now dn by dk. This is really a Jacobian. In vectors n to vectors k. And so what I'm going to get is that the sum over n goes to an integral over n, which is equal to L over pi to the dth power integral d dk. And that would be true if I'm in d dimensions. So this factor here is called the density of states in K space. And why do we call it that? Well, the formula that we derived on the other page says basically that the volume of every quantum state n in K space is L to the d over pi to the d. Okay, so now what I'm going to do is I'm going to combine these two simplifications, step 1 and step 2. So what we're going to end up with then is, if I want to compute the number of states between E1 and E2, dE of d gamma by dE, what is that going to be? So it's going to be 1 over n factorial. That was the formula that came from counting quantum states, but not quantum particles. So that was that factor. Then I've got L to the d is just the volume of the system. So, and then I've got one of these sums for every particle in my system. Here's all the particles. So then I'm going to have a factor of the volume of the system raised to the nth power. And then I've got my factors of 2 to the 3n. I also have this pi cubed down here. So I have 2 pi to the 3n down here, if d is equal to 3. Then what I have is the integral d3 k1 d3 k2 all the way up to integral over d3 kn. And then what is the thing I'm integrating? Well, it's the Dirac delta. I'm just going to write it as a Dirac delta for now. The integral from E1 to E2 of E minus h bar squared over 2m, and then the sum from I equals 1 to n of ki squared. And then integrated dE prime. So that's my final formula for the density of states, the number of states between energies E1 and E2. And so all of these terms over here, these terms here, these ones here, and these ones here, all these terms are doing is telling me what is the name of the particles that I'm summing over. Okay, but it's an integral. And then here I have this integral to do, and the momenta comes in here. These k's, k1, k2, k3, they're dummy variables of integration. How do I know they're dummy variables? Well, they are the variables of integration like so. So when we do this integral, we're going to end up with something that only depends on the limits, E1 and E2, depends on the volume, the number of particles, and some factors of 2 pi, and it will depend on Planck's constant, it will depend on n. Okay, so now let's do this. Let's have a look then at the thing that is inside here. So this thing I'm going to write like this. This is 1 over n factorial v to the n 2 pi to the 3n, and then the d by dE, this delta function, delta of E, is d by dE of the Heaviside function. So I'm going to write this thing as then d by dE of the integral d3 k1 up to d3 kn, and then the Heaviside function of E minus h bar squared over 2m ki squared like so. Okay, the inside of this Heaviside function only depends on whether the argument inside it is positive or negative. So what this is doing, I want you to think about this. This is the interior of a sphere of radius 2e over times m over h bar squared. So think about it this way. Let me draw my space like so. K1, K2, K3. These are different directions in an n-dimensional space. I want to know this thing is always going to be positive when E is greater than h bar squared over 2m sum over I ki squared. So the sum over ki squared, what does that look like? X squared plus y squared plus z squared is the radius of a sphere in 3 dimensions. So sum over ki squared from 1 to n is the radius squared of a sphere in n dimensions. So what this actually is I've got a sphere, a radius, let's call it r. And as long as we are sampling the inside of that sphere, all the possible k values will be a distance less than the radius of that sphere from the origin. And if they are satisfying that condition, then when that's positive, that just gives me a factor 1. So in fact, all I'm doing with this integral is I am calculating the volume of a sphere in 2n dimensions. So the k values inside the sphere will be a distance less than the radius of the sphere from the origin. So actually all we're doing is this is enumerating states. And then this is telling you, as I scan through all those states, that's the interior of the sphere, as long as the k values are within 2m e over h bar squared to the half radius, then they will be counted. Okay, so all we're doing actually then is working out the volume of a sphere in 3n dimensions. Okay, so that's not quite the integral that we have to do though. So that's what the Heaviside function is. But we do have it over here, if you look back on the left-hand side, we still have to operate on that with a d by dE. So in fact, what we're going to get is not the volume of the sphere, but what we're going to get is in fact the surface area of the sphere. The surface area of that sphere. That's the derivative of the volume with respect to radius. That gives you the surface area. So now I want to show you how to calculate that. So what we're going to first of all do is we're going to rescale the parameters. So I'm going to make a new variable. I'm going to define qi to be h bar squared over 2m to the 1/2 times ki. Okay, so why do I want to do that? I want to do that because I don't want to keep writing factors of 2m, h bar squared, and things like this. So once I've got that out, then what's going to happen is that now we get v to the n factorial, 2 pi to the 3n then I'm going to be changing my variable in the integral from going from d3k to d3q. And so d3k to d3q, the Jacobian of that transformation is h bar squared over 2m to the 3 halves. So what I'm going to get then is 2m over h bar squared to the power 3n over 2. And then the integral d3q1 up to d3qn times delta of E minus the sum over I of Q I squared. Okay, so that looks a bit cleaner. We've got all the factors of mass and a Planck's constant outside. All we have to do is do this integral, and you can see why this is the surface area. Okay, so whenever this thing is like the radius squared. And so whenever the radius squared reaches the energy that you've chosen, you're going to get a blip. So we're going to just count how many values of Q have radiuses that sit exactly on the sphere of radius E. So what we're counting then is this is the surface area of a 3n dimensional sphere. And the radius, well, this is the radius squared, so the radius is going to be the square root of E. Okay, so now the only thing we have to do is just do this integral. So I'm going to do this integral, but I'm now going to do it in polar coordinates. Okay, so let's have a look and see how to do this integral. So I'm going to write this integral d3q1 up to d3qn. So this, if you think about it, I've got a vector which is like this. It's got the vector q1, the vector q2, all the way up to the vector qn, and each of those q vectors has 3 components: x, y, and z. So this q, this I can write as the integral of d3n of some new vector, which I'll call q, like so. And then I have to compute the delta function. So delta of E minus q squared. Yeah, question?
Sorry, could you explain again? I'm confused what happened to the Heaviside function.
So what happened to the Heaviside function was this d by dE acted on it to give you this delta.
We had that before.
We had that before. I just went back and forth to do what the
Okay, so. Okay, now we're going back. And then
we're going back to do it. We're going back to doing it in terms of the delta function. Yes, we could go back and forth between either of them. Do you happen to know what the volume of a 3n dimensional sphere is? I didn't think so. So we're going to calculate it. Okay, one question over there.
So they have a step function because it's an inequality. Basically, it's going to keep basically everything inside. Basically.
Yeah.
So when you take a derivative, it's basically just like going back to basically what's on the surface.
That's exactly right. That's exactly right. Okay, so we're now looking at the surface here, and we only get a blip when we're on the surface. Before we got a blip anywhere in the volume. Now we're getting a blip just on the surface, and we're counting the surface. Okay, so this is a complicated way of doing a surface integral. So let's have a look at this integral. How we're going to do this integral? Well, what I'm going to do is you can see that this function is just a function of the radius in my 3n dimensional Q space. So if it just depends on the radius, then I'll just do the integral in spherical polar coordinates. So what we'll do is we're going to do this integral in spherical polar coordinates in 3n dimensions. Ultimately, n is going to be Avogadro's number of particles. Okay, so all of statistical mechanics is a very high dimensional integral. All right. Well, that's good. Okay, so let's try again. Okay, so now let's go and do this integral. So this integral then is going to equal, well, it's going to, if I do an integral in 3n dimensions, what I'm going to get is the surface area of a 3n dimensional unit sphere times the integral over the radial coordinate of q to the power 3n minus 1 dq delta of E minus Q squared. Okay, so now we've got a one-dimensional integral, which is really nice. This thing over here, this S3n, this is a symbol for a number, which is the surface area of a 3n dimensional unit sphere. Okay, so think about this. If I'm in 3 dimensions, then it's 4 pi. If I'm in 2 dimensions, it's 2 pi. And in n dimensions, it's some other number with lots of pi's and things. Okay, I'll show you how to calculate that in a minute. But for now, it's just a number and we don't really care what it is. Now you say, great, this is fantastic because everything I've got here, this is now a one-dimensional integral. So we should be able to do it, right? We started off with 3n dimensional integrals and sums, and it was all very complicated. Now we've beaten the whole thing down to 1 dimension. And so you just say, well, it's just q to the 3n, it's just a delta function. How hard can it be? Okay, well, there's a problem with this delta function. This is a delta function, but it's a delta function of q squared, not a function of q. So now we have to compute the integral from 0 to infinity, the radial variable, dq delta of E minus q squared. Okay, so the problem is that we only know that if I have an integral of f of x delta of x minus a dx, then that is equal to f of a. Okay, so that was the defining characteristic of a delta function. But what we have here is our problem E minus q squared inside the delta function. So now what? Well, so there's an answer to that. We have to make a change of variable. So we're going to use a formula, a change of variable formula, which I'm just going to write down, and we can talk about how to prove it later. So change of a variable. So here is the formula. If I have a delta function, not of q, but of f of q, where f is some function, then that is, well, you might think it's the sum when q has that when q is a root of f of q. So you'd be right about that. We have to sum over I equal the roots of f of q, because when f of q is equal to 0, then the delta function will be 0. But it's not just that. We have to divide by a normalization, and that normalization is f prime of q, the derivative of that function evaluated at each root. So I'll write it like that. So all we're doing is we're saying I've got a function, and it's a squiggly function like this, and it has multiple zeros, and at each 0, it's going to go through the origin and have some slope. There's going to be a linear term that describes that. We don't care whether it's linear this way or linear this way, so we divide by the modulus of that slope, and that's what the sum of f of q is. That's what the sum of delta of f of q is. So this is just a change of variables, and afterwards I can talk you through how to derive that. I don't want to spend time deriving that right now. So in our case, knowing that function, so in our case, so when I say the roots of f of q, the roots of f of q are f of qi are equal to 0. That's what it means. Okay, so in our case, f of q is the function e minus q squared, and that means that the roots are when q is plus or minus the square root of e. So I can write then the delta of e minus q squared is equal to the delta function of the square root of e minus q plus the delta function of the square root of e plus q, and it's normalized by this term over here, the absolute value of f prime squared. Well, f prime of q is equal to minus 2q. So I have to evaluate that at the points q is plus or minus the square root of e. And so what I get is 2 over the square root of e, and I get a plus 2 over the square root of e as well here. And I smell a misprint, but I'm not sure. Let me just check here. Okay, so I think that's fine. So that's the formula that I get. So now I have to do the integral. The only thing about the integral is I've got the formula s to the 3n, and then I also have this q to the 3n minus 1 over here. So I'm going to have to evaluate that at the value of the delta function, which is plus or minus the square root of e. So let's now do the integral. And so what I'm going to get is the surface area of the 3n-dimensional sphere, and then e to the 3n minus 1 over 2 divided by 2 over the square root of e, and that is 1/2 s to the 3n e to the 3n over 2 minus 1. Okay, so now if I put that all together, what I get is d gamma by dE is equal to 1/2 v to the n over n factorial 2m over h squared 3n over 2, surface area of the three-dimensional sphere, and then e to the 3n over 2 minus 1. So that's our formula then for d gamma by dE. And you can see that as we expected, it grows rapidly with energy. The higher the energy is, the greater is the number of states. And this is d gamma by dE, so you can simply integrate that, and that 3 e to the 3n over 2 minus 1 will turn into e to the 3n over 2. Okay, so that is how you do the calculation. We still have one more thing to do. I want to now show you, what is this factor of s to the 3n. So the next thing I want to show you is how to calculate the surface area of a unit sphere in d dimensions. So this is a beautiful trick. It's just a math trick. There's nothing special about it. It's just a number, but we're going to calculate what that number is. So here's what you do. You just say, here's the integral I want to do. I want to do this integral, the integral d dq e to the minus q squared. Okay, where q is a d-dimensional vector. Okay. How many people here have already done that integral right now, since I just put it up? What do you think is the answer?
Oh, you're looking at me.
Well, you were the only one who was brave enough to put your hands up.
Something too
Something 2 pi. Well, let's think about it. If d was equal to 1, what would this integral be? Well, this is an integral from minus infinity to plus infinity. So you're on the right track. What you were saying. Root pi. Well, no, or something. Root pi. Okay. But then I've got this integral factorizes, right? This factorizes as the integral dq1 dq2 up to dqd, and then e to the minus q1 squared, e to the minus q2 squared, etc., etc. So this thing is just going to be root pi to the power d. Right? So you were pretty close. That's what you were thinking of, right? Right? Okay. So that's how you do that integral. Okay? All right. Now we're going to do it a different way. So we want to remember that I want to work out the surface area of a d-dimensional sphere. I want to work out the surface area of a d-dimensional sphere. What calculation could I do which would involve the surface area? Well, the obvious thing to do is, so here what we did in our heads, we did this in Cartesians. So now let's try to do it in polar coordinates. Okay, so if I were to do this integral in polar coordinates, what I would do is I would say, well, I'm going to go into polar coordinates. So it's going to be the integral over solid angle in d dimensions. Then there's going to be the integral over radial coordinate, 0 to infinity, q to the power d minus 1 dq. And then the thing I'm trying to integrate is e to the minus q squared, which just depends on the radial coordinate. Let me just I just want to double check that everybody understands. Does everybody understand why this is q to the power d minus 1? You do? Right, okay. All right, suppose I've got the integral d3x. So the integral d3x in polar coordinates is the integral 4 pi r squared dr, and r goes from 0 to infinity. So this 4 pi here is the surface area of a three-dimensional unit sphere, S3, and it's r squared dr, right? You learned that on your mother's knee. So if it was in d dimensions, that's that 2 is equal to 3 minus 1. So if it was in d dimensions, it would be d minus 1. Because I'm just doing the radial dimension, and then there's d minus 1 other dimensions, which are not radius, which are orthogonal to that, which are the solid angle. So that's why it's d minus 1. Okay? So when you so now you just say, well, let's have a look at how to do that integral. So we can beat this integral into a familiar form by making x be the variable q squared. Okay, so why do I do that? Well, if I make that change a variable, then if you do the calculation, what I get is I is equal to now the surface area of a d-dimensional sphere, the integral from 0 to infinity, x to the power d minus 1 over 2, e to the minus x, and then 1/2 dx over the square root of x, just doing the change of variable. And so if I do that, then you notice, if you've seen it before, you'll notice this, that this thing here, this integral, this reminds you of what's called the gamma function. Let me write it down for you. So gamma of z is not the gamma, has anything to do with statistical mechanics. This was written down by Euler in 1780 or something like that. So this function is just defined as 0 to infinity t of z minus 1 e to the minus t dt. And this function is equal to the factorial function when z is an integer. And when z is not an integer, so z is 3.75, you'd say, how could you have 3.75 factorial? Well, the answer is you can't if you think 3 factorial is 3 factorial, 3 times 2 times 1, but you can extend it into the complex plane, and this is the formula that does it. So this is Euler's gamma function. And so this integral here, this integral inside here, inside our thing over here is indeed Euler's gamma function. So I can then say, if I put the pieces together, that the integral that I want to solve is equal to 1/2 times the surface area of the d-dimensional sphere, and then Euler's gamma function of d over 2. And you can check that you've got this square root here, that square root goes with that one, the half is this half over here, and so I get half the surface area of a d-dimensional sphere times gamma of d over 2. But we already calculated what that is. We already calculated that this integral I is equal to pi to the d over 2. And so therefore, the surface area of a d-dimensional unit sphere is 2 pi to the d over 2 divided by the Euler gamma function of d over 2. And that's a number that you can evaluate now in d dimensions. Okay, so now I want to go back to statistical mechanics. Okay, so most of this lecture has just been some awful, horrible calculation that how many people have seen this calculation before? Nobody, okay? Yeah, not really, yeah. It's a horrible calculation, okay? And the reason I've showed it to you is, first of all, that you can do this calculation. It's not that horrible, it's just something you can grind through. But what we're going to be doing in the rest of the course is we're going to be finding ludicrously simple methods to do calculations just like this, without doing it. Remember, this was the simplest possible case. It's a quantum gas, and it has no interactions. And that's already sort of made our brains explode. Okay, so what would happen if we had to look at now particles with interactions and all sorts of things like this? It would be horrific. So there's easier ways to do these calculations. But the purpose of this is to show you what is the calculation that we're trying to do, so that then we'll appreciate how to get the calculation right. So there's the other thing about this calculation, which I'm going to show you. And so let's now go ahead and jump in and do that. And I'm going to follow my handwritten notes because they have less mistakes in terms of typos and things than the typed notes. But and I may be making a correction on the fly. So if I get a factor of -1 or something wrong in the formula I'm going to show you, please understand why that's the case. So now the next thing I want to do is I want to compute the thermodynamics. And we've done all the work, so it actually isn't hard. So let me write down our formula for d gamma by dE, which I think is this: v to the n over n factorial 2m pi h squared, that's an h, not an h bar, 3n over 2 e to the 3n over 2 minus 1 divided by gamma of 3n over 2. Okay, so that is the formula that we've got. I'm going to compute the entropy, which is k log d gamma by dE delta E. So that's that's the entropy that we want to compute. We're going to use Stirling's formula, which says that if I want to compute the logarithm of x factorial, that is the large X, x log x minus x. So that's what that says. And so therefore, if I now compute the entropy, what that's going to be is KB. I'm now going to take the logarithm of all of this. So let me just write down the answer. KBN into logarithm, natural logarithm of V over N plus 3 halves log 4m pi e over 3n h squared plus 5 halves plus a correction term of order log of n divided by n. And that's the final formula for the entropy. Okay, now let's see if it works. Okay, so remember that we discovered last week that 1 over temperature is ds by dE. So if I take the derivative of the entropy with respect to energy, you can see that there is the only place E occurs is in the middle term, and it's multiplied by a factor of 3 halves. So I have to expand this logarithm, take the log of that. So what I'm going to get is that tells me that E is equal to 3 halves n kBT. If I then compute what the pressure is, so the pressure is T ds by dV at fixed E, then the pressure that I got to compute the derivative of the entropy with respect to the volume. Where does the volume occur? It occurs in this first term over here. So then what I get is the P is equal to N K B T over V. In other words, PV is equal to N K B T. So now we've derived these formula for our ideal quantum gas. Okay, you've seen those before, right? Okay. Okay. Are you surprised by anything? Where did you see these formulae before? I know you saw it in a previous class. Yeah, I know that. But what system had these things? Say it again? Yeah, say it again. The ideal gas. Yeah. Which ideal gas? Classical ideal gas. Yeah. That's where you saw those formula. But were we computing the classical ideal gas? No, we were supposed to be computing the quantum ideal gas. So we got the wrong answer. So here's the story. So we formulated the problem, we used quantum mechanics, we did the calculation, we wrote it down in terms of quantum states. We then we used our principle, we figured out how to do the calculation, we did the calculation, we did it, everything we did it in a completely kosher way. I showed you all the changes of variables and the integrals and everything like that. And in the end, we got the wrong answer. We got the classical gas. Okay. So what was our mistake? So first of all, is it the wrong answer? And so here's two questions. Question one, is it the wrong answer? And question two, if so, why? Where did we go wrong? Okay, let me convince you that it's not the wrong answer. Okay, so we got the equation of state. We got PV as nKT. We got the energy as 3/2 nKT. But if you look at our formula for the entropy, is that formula for the entropy what you would get from classical mechanics? When you said that we had done the classic. This is the formula you get for the classical gas, and you're absolutely right. But if you look at our formula for the entropy, is that the same formula that you would get for the classical gas? You're shaking your head. Why not?
Well, there's an H in there.
It's got Planck's constant in it. Yes, it's got Planck's constant in it. So this does have something it must be something, right? What do you think it is then, if it's got Planck's constant in it? Everything you said is completely right. So what do you think is the interpretation of what we just calculated?
I mean, it's just that I guess we didn't consider other effects of quantum. All that would consider.
Say it again.
We didn't consider all the effects for like quantum mechanics, kind of, and it's not interacting, so it's kind of just the same exact thing as the classical, almost.
Somewhat. There is something that we didn't take into account. There is something we didn't take into account from quantum mechanics. You're absolutely correct about that. Can anybody tell me what it is? Okay, let me just, you already know?
No.
Okay. So remember that we're doing the quantum ideal gas. These are ideal particles, but they are identical particles. A light bulb went on down here, right? What can you do you know what we did? Yeah. You just I'm not picking
Well,
up.
okay, someone at some point last week said you can't label the states if it's a quantum they're identical particles in the quantum system, and
Mhm.
something fermions and something.
Okay, right. So what do you know from your quantum mechanics class is that when you have ideal particles, they come in two types, fermions and bosons. Fermions have antisymmetric wave functions under exchange. Bosons have symmetric wave functions under exchange. And what did we do here? We didn't worry about that. We completely forgot about it. We included all the wave functions. Okay. Now, when does the distinction between fermions and bosons not matter? It definitely matters at very low temperatures, right? Where you're more or less in the ground state. Ground states of bosons, the ground states of fermions are very different. But if I go to very high temperatures, all the atoms in this room are quantum mechanical, but you wouldn't know it. They're behaving classically. Why? Because you're at very high energy levels, and you know from doing quantum mechanics that when you go to very high energy levels, then you'd use the WKB approximation and things like that, and you get into this semi-classical regime. So what we've actually calculated is we've done the calculation of the ideal quantum gas, but because we threw away the wave function symmetry or anti-symmetry, what we've computed is what is the right behavior in the high temperature regime where so many states are occupied that it doesn't matter whether they're symmetric or anti-symmetric because there's so many states are occupied. So all of those quantum distinctions that matter at low temperatures are no longer having an effect. And that's what we've calculated. So we've got a formula, which is the correct semi-classical formula. This is what you would get if you took the exact quantum mechanical calculation, which we'll do later, and then were to expand it, like doing a WKB approximation, to find what is the connection to the classical limit, the semi-classical result, as we call it. So that's what we've calculated. So let's just end then by summarizing that. So is it the wrong answer? Well, the answer is to that, yes, it is the wrong answer. And if so, why? Because we forgot about the symmetry of the wave functions for identical quantum particles. So this formula has a name. This formula it was a great triumph of early quantum mechanics. This is called the Saka tetrode formula. And I think it was discovered in, I don't know, 1928, something like that. Okay, so we're going to end here. And at 4, we will go to, those of you who want to, we will meet to have our discussion room. I'll be happy to answer any questions. I will invite you to do the calculation in the homework where you're going to repeat this calculation, but do it using periodic boundary conditions rather than zero wall boundary conditions. And it'll give you an opportunity to go through the calculation, find all my minus sign mistakes and factors of 2 and things like that, which inevitably got in contaminated the notes. Okay, so I'll be able to take any questions there at the discussion session too. All right.